everyone, welcome to GemChem. Now today's video is on solid state part 8 video, and here we will deal with voids in closed packed structures and defects in crystals. Now before starting, if you have not watched the previous videos on solid state, you can watch it. I will give the link in the description box as well as the I button present above this video. Now before going to this video, if you are new to GemChem, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. Now what do we mean by voids? Now voids generally refers to the unoccupied or vacant sites present in the lattice of a crystal. Now there are two types of voids, that is tetrahedral and octahedral voids, and these voids are also known as holes or interstices. Now if we consider for the tetrahedral void, so in tetrahedra we place three spheres in the bottom and one above. So if we consider this sphere to be in the above portion and these red spheres to be in the down portion, then what happens? There is a creation of a hole or a void which is known as tetrahedral void. So if we consider this to be a tetrahedra, that is, this is a tetrahedra, if we join these points and these points, then there is a hole created in between, and this is a tetrahedral hole. Now if we consider for the next part, that is octahedral hole, then octahedral void is created by three spheres up plane and three spheres down the plane. So the void generally looks as a octahedral void. Now we will deal with these two kinds of voids in details. Now tetrahedral voids are the vacant space surrounded by four nearest neighbors in the tetrahedral disposition in the crystal lattice and is called tetrahedral void. So we can see that this void is being surrounded by four particles. Whereas if we consider for the octahedral voids, then we can see the vacant space surrounded by six nearest neighbor in the octahedral disposition in a crystal lattice is called octahedral void, right? So we can see that there is six neighboring particles present around this particular void. Now if we consider in the closed packed structure, the number of tetrahedral voids will be double the number of constituent particles. So you have to remember this, that the number of tetrahedral voids is actually double the number of constituent particles present within. And in the closed packed structure, the number of octahedral void is same as that of the number of constituent particles, because every void is surrounded by six particles and there are six voids around each particle, whereas in this case there is every void has four particles and every particle is being surrounded by two voids, so there are 8 voids around it. Whereas the radius of the tetrahedral void is 0.225 times the radius of the constituent particles, whereas in this case the radius of an octahedral void is 0.414 times the radius of the constituent particles. So we should remember that the void which is larger here is actually octahedral void. Okay. Now we will deal with the defects in crystals. Now defects are being classified into two broad classes, that is point defects and extended defects. Now extended defects is classified into line defect, which is further classified into dislocation, and there are two types of dislocation, that is edge and screw. But we will not be concerned with this kind of defect because this is an advanced level treatment. We will only deal with point defect. Now what is an extended defect? In short, it is the defect occurring due to the irregularities due to the stacking of the planes in the lattice. Now point defects occurs if the deviation occurs because of missing atoms, displaced atoms or extra atoms, and the imperfection is specifically known as point defects. Now this point defect is being classified into three kinds of defects: intrinsic, extrinsic and non-stoichiometric defect. Now intrinsic defect is further classified into Schottky defect and Frenkel defect. Extrinsic has no classification, whereas non-stoichiometric is being further classified into metal excess defect and metal deficiency defect. Now if we focus on this metal excess defect, it is classified due to the anion vacancies and due to the interstitial cations. Now we will deal with the point defect in details. Now let us see. The point defects are the defects occurring at the specific points in the lattice where a particular ion may be absent or a particular ion is present but it is not expected to be there. So as I told you that it is not expected to be present there, or it is present in excess, right? Or it is not present, so it causes a defect in the crystal. Now we will deal with the two kinds of stoichiometric defect, or more specifically intrinsic point defect. Now see, Schottky defect and Frenkel defect. Now this defect arises when equal number of cations and anions are missing from the normal lattice sites. Now see, this is a regular lattice, so here there would have been a B minus, and here the down portion there would have been a plus, but there is a vacancy created by missing anion and vacancy created by missing cation. Whereas in Frenkel defect, this defect arises when the cations leave their lattice sites and occupy interstitial sites between the lattice points. So we see that A plus should have been present here, but it is occupying a interstitial void or interstitial site. So we can say that this is a vacancy created due to the cation missing from its site, and this is a missing cation occupying the interstitial site. Now we will see other differences between the Schottky defect and the Frenkel defect. Now this causes decrease in density of the crystal, whereas this does not affect the density of the crystal. Here it is common in the ionic compounds with high coordination number, where the size of cation and anion are comparable or almost equal, whereas this kind of Frenkel defect occurs in the ionic compound with low coordination number, in which anions are larger than cations. And always remember, this is common also in covalent compounds. It has no dielectric effect on the dielectric constant, whereas it increases the dielectric constant of the crystal. Now if we consider this one, electrical conductivity not affected, and here the neutrality is also not affected. And examples for the Schottky defect are NaCl, KCl, KBr, CSCl, AgBr, CEO2, that is cerium oxide, and thorium oxide. Whereas in this case it is ZnS, AgCl, AgBr, AgI. If we look carefully, we can see that Schottky defect and Frenkel defect both occurs in AgBr, right? Now what do we mean by extrinsic defect? Now I hope everybody has known about the term of doping. So this occurs when doping occurs. Now if we consider a lattice consisting of Zr4 plus, O2 minus, again Zr4 plus, and O2 minus. Now if we consider this whole lattice again and again, then it will be easier for us to understand what is going on. So we are drawing the lattice. Zr4 plus, O2 minus, Zr4 plus, O2 minus. Now this is the lattice and this will continue. So now if this lattice is being doped by 1% calcium oxide as dopant, then what happens? One of the anion is being lost and one of the cation's position is being occupied by Ca2+. So if we draw the lattice again, then it would look like this. That is, this side becomes vacant and this side gets occupied by a calcium 2+. In order to maintain the electrical neutrality, this O2 minus gets lost. So in this above case, some of the Zr4 plus ion is being replaced by calcium 2+ ions, and in order to maintain the electrical balance, equal number of neighboring oxide ions leaves the lattice. Thus the number of calcium 2+ ions attached is equal to the number of anionic vacancies. Okay, so this is extrinsic defect. Now we will deal with metal excess defect. So we know that this is a non-stoichiometric defect. So this type of defect arises when an anion is being missing from its lattice site, creating a hole, and this hole is being occupied by an electron, and this electron maintains the electrical neutrality of the crystal. Now the electrons trapped in the anion vacancy are called F centers, or more specifically Farbe centers, F-A-R-B-E, Farbe centers or color centers. Why they are called color centers? Because they impart color to the crystal. The trapped electron absorbs the radiation or the light and get excited to a higher energy, thus imparting color to the crystal. Now, this is the F center occupying the space of the missing anion, and due to the F centers, KCl appears violet and SiCl appears to be pink. Okay, otherwise KCl and SiCl should have been colorless, right? So now we will go for the next category where there is metal excess defect due to interstitial cations. Now if we look carefully, there is an extra cation and there is an electron. So this type of defect arises when an extra cation is present in an interstitial site and the electrochemical neutrality is maintained by the presence of an electron some other nearby interstitial site. Okay, now we will deal with the most important question, that is, what happens when ZnO is heated and further allowed to cool at room temperature? So we have to answer this question, and this question often comes. So right now first we are concerned with drawing the lattice. Okay, so we draw the lattice as Zn2 plus, O2 minus, then Zn2 plus, then O2 minus, right? And again O2 minus, Zn2 plus, and O2 minus, Zn2 plus. Now Zn2 plus, O2 minus. Here we keep a blank. Why we keep a blank? Let me tell you after drawing. O2 minus, then Zn2 plus, then O2 minus, then Zn2 plus. Now this crystal ZnO is particularly prone to Frenkel defect. Since it is covalent, upon heating, some of the oxide leaves the lattice. Now first listen to first point carefully. It is prone to Frenkel defect. Now what is Frenkel defect? We have already seen that in the Frenkel defect there one cation leaves a site and stays in the interstitial site. So we will consider one of the sites to be blank and put that Zn2 plus in the interstitial site. So if we put the Zn2 plus which is missing from the site as here Zn2 plus. Now what happens? Upon heating, some of the oxide ion leaves their position from the lattice and forms molecular oxygen by loss of electron. This electron lost during the process are transferred to suitable interstitial sites and these sites behave as F centers. Now if we lose an O2 minus, then what we get? Let us see. Then it will be half O2 plus 2 electron, right? So now we draw the new lattice, that is Zn2 plus O2 minus Zn2 plus O2 minus, and here O2 minus Zn2 plus, a vacant site created when O2 minus has left, Zn2 plus and Zn2 plus here, O2 minus again here. Here is a vacant site due to loss of cation and Frenkel defect, O2 minus, and the last remains same, O2 minus, Zn2 plus, O2 minus and Zn2 plus. Now here we have a Zn2 plus, right, as previous one, and what extra we have? We have now the electrons which are being released from here in the interstitial sites. 2 electrons present in the interstitial sites. Now the system may be considered to be a particle in a box problem and the yellow coloration is being observed due to the electronic transition in the visible region. Now on cooling, molecular oxygen is absorbed by the lattice and the electron from the F centers are transformed to the molecular oxygen and thus it is converted to oxide, and these oxide ions will now occupy the anion vacant sites that are formed when they left. So the lattice sites, initial lattice sites which were formed upon cooling are now no longer being the F centers, and it is for these reasons that such lattices regains the original white color. Okay. Now we will deal with the metal deficiency defect. Now what happens in this case? This defect arises when a cation is missing from its original normal lattice site and the charge is balanced by nearby metal ion having higher positive charge. So here a cation is being missing and this cation has 2 positive charge to control the electrical neutrality. So this is the missing cation and this is the cation having greater positive charge. So now this was the end of the topic of solid state. Hope it was helpful. If you need any kind of help on this and any extra topics needed to be covered, you can tell me using the comment box. Now this much for today. Thank you for watching. Do not forget to like, share, subscribe and comment.